In this module we're going to be investigating the Laplace transform and the inverse Laplace transform. First I'll go through an example in MATLAB of finding the Laplace transform and then the inverse Laplace transform. And then I'll cover page 228, problem 310, which is part of your lab. I'll work through part A and I'll leave part B for you, and then the remainder of the lab for you as well. So again, I have a text file here just to make it a little bit easier on me in terms of typing. Go ahead and put a sample function in. And this is just going to be a comment. So we're going to find the Laplace transform of a function of t equal minus 1.25 plus 3.5 t times e to the negative 2t power plus 1.25 times e to the negative 2t power. And you can go through and work through the Laplace transform of this. But in terms of MATLAB, the first thing I'd like to do is, since we're going to be using and taking advantage of symbolic calculation or computation in MATLAB, we needed to find some symbolic variables t and s. Okay, once that's done, then we need to be very careful in how we put our function of t into MATLAB. And if you look real carefully, you can see how I've put this function in there for our original function of t. And then we're going to utilize the Laplace function of MATLAB. I'm going to set that equal to f. Here I'm not going to put the semicolon because I'd like for you to see what it generates based on the parameters f, the function, and then the variables t and s. So we see that we have Laplace transform, which it can be simplified a little bit. So if you were working this on paper, you certainly would simplify it. So we actually have a command for that. So we just simplify the Laplace transform. And now we have reduced that somewhat. And then we have another function that will allow us to put it in a more readable format, much like what you would write on paper, and that's the pretty command, which basically gives us this type of output. So what we have is s minus 5 over the product of s times the quantity s plus 2 to the second power, and that's pretty readable format. So what if we want to go the other way? We like to find the inverse Laplace transform of the function. Say we're starting out with our f of s function here, s minus 5 over s times the product of s plus 2 to the second power, and we'd like to go the other way and obtain our original function back. So we're going to be arriving at a function in time. Okay, so again we put in our original function here. Go ahead and define our symbolic variables t and s. And we have a function called I Laplace, inverse Laplace, of our function f. And again, I'm going to go ahead and leave the semicolon off so it echoes to the screen. And there we have an answer. And we can simplify the answer, which is always recommended. Echo that to the screen. In some cases it may or may not simplify very much if it's already in a simplified form, but nevertheless I still would recommend that. And then we would use our pretty command again to make that a little bit more readable. And if you look very closely, you can see the order is a little bit different, but it is the original function. We have minus, and then 5 divided by 4 is going to give us 1.25. And then we're going to have 7 divided by 2, which is going to give us our 3.5 t. And we're in the denominator here, but if we put that in the numerator, you're going to have a negative exponent. So there's our e to the negative 2t. And then we're going to have the 5 divided by 4, which is 1.25, times the product of, again, expressing that in the numerator, we're going to have e to the negative 2t. And so what we've done is we've arrived back at our original function. So we see that we have successfully performed the inverse Laplace transform. Now moving on to problem 310, part A. Just for good measure, go ahead and just clear everything out of memory. Okay, so we're going to use MATLAB to compute the inverse Laplace transform of, and you can see on page 228 they give us x of s, and it's a pretty involved function there, and so we have s squared plus 2s plus 1 over a product of the denominator. And while you can go ahead and multiply by hand the 3 different polynomials in that denominator, the conv function can be used to obtain the coefficients of the product of the 3 polynomials. So I'll demonstrate that. You do this in 2 parts. You set a variable equal to the denominator. And the first part of that's going to be it's going to be the s times s plus 1. So this is the s part, the 1 and 0, and then the coefficients of 1 and 1 represent the s plus 1, and then you take the result of that, which is stored in den, and then you perform the same operation using the conv function, multiplying that times the coefficients of s squared plus 10s plus 50. So that's the 1, the 10, and the 50. Okay, so that's our denominator. And then we define let me define the variables s and t. And here I'm going to use the Laplace function again, and we're going to put the function directly in this time. So I would recommend that you study real carefully the way in which I put this function in, but basically it's the function that they gave you in the textbook. So there we have arrived at a function of t, and then we can plot that function. And there we have it. And then you can adjust the labeling and so forth. But this is basically the output, and it's what we're wanting to arrive at. Okay, so you would basically take a screenshot of your code and the output waveform of the plot, and you would include that in a Word document with course, the remainder of the lab. And that will complete Module 4 lab, and I will see you in the next.